Go. So today hopefully we're going to discuss more of magnetic fields and magnetism. Still we've not reached the point to discuss magnetic materials, but this is probably the third lecture on magnetic fields. Today a homework is going to be posted. That homework is due next Tuesday by 5 p.m. and the quiz is going to be next Friday. So I would like to introduce to you a machine that is called the cyclotron. Now the cyclotron was invented in the 1920s by Ernst Lawrence. What the cyclotron is that it's basically a particle accelerator. And some of the most significant experiments in particle physics which help us understand our universe are performed on experiments on equipment of this kind, including the Large Hadron Collider in CERN. So how does a cyclotron work and what is it constructed like? The cyclotron basically comprises two hollow metallic hemispheres . Okay, now these are metals and they are hollow from the inside. So if you look at the edge of one of these chambers, so this is our hemisphere, and if you look at the edge, it has a slit. Okay, so particles can go in and come out. Okay, so there's a window and it's hollow from inside and the rest is all metal. And we know that inside a conductor the electric field is zero. Inside the interior of a conductor, if you have a hollow metallic conductor, all the electric field is outside. There's nothing inside. In the annular region there is no electric field. Now what we have is a particle that goes round and round and round in circles inside this machine. But before that, we'll have to see how a particle behaves inside a magnetic field. And we've already seen that the force exerted on a particle of charge q moving with a velocity v is given by qv cross b. This is the Lorentz force. And this force is normal to both the instantaneous velocity and the magnetic field. Suppose I have a magnetic field that's pointing out of the plane of the blackboard. Okay, and it's a uniform field. The field is constant everywhere, both in magnitude and direction. So the field is pointing out. So B is out of the paper and I have a particle, a positively charged particle such as a proton that is moving with a velocity to the right at some instant. The velocity is v vector and it's moving towards the right. Now a force is going to act on this particle at this particular instant. What's the direction of the force? Upwards or downwards? It's downwards. So I point my fingers in the direction of the velocity, the field is outside, I curl my fingers out and the thumb is pointing downwards and I have to use my right hand because it's a positively charged particle. So the force at this instant is pointing downwards. Just at this instant. Okay? Let's call this instant P. Now the force is normal to the velocity and it's normal to the magnetic field. So as a result of this force, this particle will move downwards. It will occupy a new position. The net result is that this particle will start moving in a circle. Okay, because the force is always normal to the velocity and the velocity is always tangent to the circle. So this is circular motion. So at each point on this circle, the velocity is pointing in a certain direction, v, and it's tangent to the circle. So the yellow vectors represent the velocity at each point. And these yellow vectors also represent the momentum at each point. Okay, so these are the momentum vectors on the circle. This is the momentum of the particle at any instant. Okay, P. This is P. This is P1. This is P at some other instant. This is P at some third instant, and so on. So the momentum, the linear momentum, is always tangent to the circle, and the force is always normal to the momentum. So these green arrows represent the force at each instant, and since the radius is normal to the tangent, the green force is pointing towards the center of the circle. So it is providing the centripetal force that is required to keep this object in motion. Okay, so this is the force that acts on each instant. On each instant, the force is changing its direction. It's always pointing towards the center, but here the force is in this direction, here the force is in this direction, so it's radially inwards, but all of these vectors have different directions, but the same magnitude. Now what we would like to be interested in is finding the radius of this circular motion, provided we know the magnetic field and we know the initial velocity with which the particle is issued into this region of uniform magnetic field. Okay, so it's a classic problem in circular motion. We already know that the force is equal to the rate of change of momentum. Okay, at any instant. So the momentum is different all along the circle, and the momentum is a vector. So we're taking the derivative of a vector here. Now if this vector has a magnitude, okay, this is the magnitude, it must have a direction, p hat. This is what a vector means. So if I would like to take the derivative of this vector, I have to take the derivative of the magnitude and the derivative of the direction. Okay, because both of these quantities compose the vector, the magnitude as well as the direction. So I would like to write the force as the derivative of the magnitude itself, okay, into the unit vector p. Okay, the unit vector has a magnitude of 1 plus the magnitude of p into the derivative of the unit vector. Okay, so this is a vector because this is a vector, and this is a vector because this thing is a vector. The derivative of a vector is also a vector. Now if the magnitude does not change, if the magnitude of the momentum does not change all along the circle, because at each instant the magnetic force is normal to the momentum, this term will always be 0. Okay, so what I'm left with is that I need to find out the magnitude of the momentum and the derivative of the unit vector. Okay, so this is the magnitude of this is the force vector, and if I would like to calculate the magnitude of the force, the magnitude of the force will simply be Q V B sine of theta 90 degrees. Okay, this is the magnitude of the force from the Lorentz relationship. Okay, G.
Sir, in that expression we are taking the derivative of p hat, magnitude of p hat.
Oh sorry, we take it's the derivative of p hat. Sorry, it's not the magnitude of p hat, it's the derivative of p. Okay, so this is the force. The magnitude of the force is QVB. The angle between the velocity and the magnetic field is always 90 degrees, so the sine of 90 is always equal to 1. Alright. Now what I am interested, and this must also equal P vector's magnitude and the magnitude of this derivative. Okay? Do you agree with me on this point? The magnitude of this force equals this magnitude. It's already a magnitude, and the magnitude of this vector, of this derivative of a vector. Now if this is a unit vector, is its derivative also a unit vector? Is the magnitude of the derivative also 1? No, not necessarily. Okay, so I have QVB equals this momentum into the magnitude of the derivative of the unit vector. Now I am interested in finding the derivative of the unit vector. Okay, how do I find this derivative? That's quite easy to do. If I look at the circle and I take 2 points on the circle, this is the center of the circle, this momentum is P1 vector. Okay, this point is P. Let's take a nearby point Q. The momentum here is pointing in a different direction. P, this momentum is P2. The momentum is always tangent to the circle, by the way. Okay, so I'm taking 2 close by points P and Q. I connect these points from the origin of the circle. This is R radius, this is R. Suppose this angle is delta theta. Okay, this is the angle the object has moved from P to Q in some time delta t. Okay, delta theta is the angle through which the object has moved in time delta t. Alright, now if I look at this PQO, OPQ, I can draw a triangle. Okay, OPQ is a triangle. Okay, in which P and Q are joined together by a line segment, by a straight line. If P and Q are relatively close to one another, then this arc, which is represented in white, coincides with the blue line. Okay, if P and Q are close together, then this white arc becomes the same as this blue line. Okay, so now we have a triangle. Now this is one side of the triangle, this is another side of the triangle. This vector is normal to this radius, and this vector is normal to this radius. Agreed? Because these yellow vectors are along the tangent. आप इधर नहीं देख रहे, कुछ समझ आ रही है? So what is my next argument? What should I say the next? आगे मुझे क्या कहना चाहिए? अगला जुमला क्या होना चाहिए? क्या होना चाहिए अगला जुमला? चले आप बताएं, अगला जुमला क्या होना चाहिए मेरा? What should be my next line of argument? What I've done is I have 2 blue lines and I have 2 yellow vectors, and this is a triangle. What should I say next? What should I say next? Please raise your hand. Ji. Is going to be delta theta. Excellent. Excellent. This means that if I make this triangle, then if I can make another triangle which has P1 as one of its sides and P2 as the other side, okay, then the angle between these sides is also going to be equal to delta theta. Because P1 is normal to this radius vector, P2 is normal to this radius vector. The angle between the radius vectors is delta theta, so the angle between these tangents must also be delta theta. And if I join these points through another vector, then this blue vector is simply P2 minus P1. And this is the change in momentum. And this is the change in momentum in unit time delta t, in time delta t. If the object moves from P to Q through an angle delta theta, which happens in time delta t, then the change in momentum, this same change in momentum is observed in the same amount of time delta t, because this angle is also delta theta. So these two triangles are similar triangles. Now if I have these similar triangles, I know what this length is. This is the change in linear momentum and it's a vector. Now if I know my angular velocity omega, then delta theta equals omega delta t. Okay, and I can look at these similar triangles and I'm able to write what's the length of this segment, r delta theta. So this segment has length r delta theta. I can divide this by this delta theta. Okay, then I can take this length, alright, r delta theta, this must equal this length, which is delta p. Okay, instead of delta dividing by delta theta, I take the ratio of two sides. So I have this side which is r delta theta, I divide it by this side which is r. Okay, now I take this triangle, I take this vector, its magnitude is delta p. I divide this by this length, p1's magnitude, which must be equal to p2's magnitude. So I just write the magnitude of p here. Okay, so this is just by comparing two similar triangles. The ratio of the equivalent sides is equal. So this r cancels out. I am left with delta theta, but delta theta equals omega delta t equals delta p magnitude over p's magnitude. Okay, so I have replaced the magnitude of this vector is the same as the magnitude of this vector. So I call both of these p. Okay, now what do I get from here? I get the magnitude of the change in momentum delta p over delta t. This is simply the magnitude of p into omega, the angular velocity. And if I take the limit that delta t is really small, then this left hand side is simply the derivative of the momentum vector dp over dt. This equals p omega. Alright, so but this is just the net force that is acting on the particle. And this must equal this value. Okay, this must equal the magnitude of the p vector, and for omega this is d by dt of the unit vector. Okay, so now what we have here is that there is a force acting on the particle, and the force equals the angular velocity times the magnitude of the momentum. Okay, I give you half a minute just to look at this and see if it makes sense. See if this derivation is clear to you. Alright, so now this is the net force that is acting on the particle. It equals the momentum of the particle, its magnitude, which does not change throughout the circular motion. The magnitude doesn't change, multiplied by the angular velocity. But this object equals QVB. Okay? So QVB equals P omega. This is the velocity of the particle. Now the particle can be moving with small velocities, high velocities, any velocities up to the speed of light. So it can be a relativistic particle. So if you look at relativistic objects, the magnitude of the momentum is given by, what's the magnitude of the momentum for a relativistic particle? Mechanics course, modern physics course. Gamma mv. ओके, ये देखा नहीं आपने कभी? ये कैसे हो सकता है जी? ये ओमेगा की वैल्यू होगी, ये वैल्यू। सॉरी, नहीं, बिल्कुल नहीं। So this is the, if I ignore this gamma, is this the momentum of the particle? M times the speed. For relativistic particles, I have to include this factor of gamma. This gamma is defined as 1 over 1 minus V over C whole squared under root, right? Haven't you seen this factor? So this is just the relativistic mass into the velocity, or the rest mass into the speed into this relativistic correction, the relativistic factor. Okay, so this is the momentum of the particle at any speeds. If V is really small, if this V is much smaller than the speed of light, this is just 0, so gamma is just 1, so you get the classical Newtonian formula back. Okay, so the momentum depends upon the velocity in this complicated way. If you have particles that approach the speed of light, then you simply cannot use m times the speed. You have to use this relativistic correction. And achieving particles close to the speed of light is not difficult at all. Even in a cathode ray oscilloscope, you have speeds approaching 10 to 20% of the speed of light for electrons. Okay? So it's not something out of this world. So this is the momentum of the particle multiplied by the angular speed is related to QVB. Now omega, I can express omega in the following form: V over R. Okay, the angular velocity is V over R. This is QVB. Okay, so you know this formula: V equals omega R. Okay, so omega equals V over R. I can replace this omega by V over R. So when I make this replacement, I get this V simply goes away, and I'm left with R equals P over QB. Okay? And if P is given by gamma mv, so I can write this as gamma m times the velocity over QB. Okay, and if gamma equals 1, for slow particles, this equals mv over QB. Okay, so this is the radius of motion. If you are at low speeds, it's proportional to the speed. R is higher if the momentum is higher, and it also depends upon the charge to mass ratio. Okay, so this is the charge, this is the mass of the moving particle. It also depends upon the magnetic field. Higher the magnetic field, smaller will be the radius. Higher the momentum, bigger will be the radius. Okay, now this term omega, if you observe, can you find out whether omega, the angular speed or the angular frequency, depends upon the radius r. Could you please figure this out for me? Whether the angular frequency depends upon the radius r. Please do it on your notebooks.
Angular velocity or angular frequency?
d theta by dt. Isn't it the same thing? V by r. तो v भी तो डिपेंड कर रहा है r पे. dp hat over dt.
फर्स्ट लाइन में
वो मैंने वहां से उठाया ना, वो लेफ्ट ब्लैक बोर्ड से, यहाँ से, यहाँ से. Yeah, but yeah, and it's also equal to v over r. It's independent of the radius.
अगर हम मतलब v is equal to omega r से करें फिर तो मतलब
Sorry?
working it out.
Good. Alright, so here the frequency, the angular frequency or the angular speed, omega, is simply v over r. But this velocity depends upon r. Through this relationship, r equals this. So I will take v divided by r. R is now equal to mv qb. So this v goes away. Omega equals qb over m. So this is the angular speed or the angular frequency. Higher the magnetic field, higher will be the angular speed. But interestingly, the omega does not depend upon the radius. So how is that possible? The inverse of omega is the time period. 2 pi over t is omega. How is it possible that a particle that's making a big circle, because it has a bigger momentum means a bigger circle. How is it possible that a particle making a bigger round trip in a magnetic field has the same time period as a particle making a smaller round trip? Because the velocities are also proportional to radius. Bigger radius, bigger momenta, bigger velocities. So even though the particle is making a big circle, it's moving, traversing the big circle with a higher speed, so it takes the same amount of time. It's just like a pendulum that is undergoing simple harmonic motion. The time period does not depend upon the amplitude of oscillation, providing the amplitude is not too large. So all of this discussion, if you notice, is valid for gamma equals 1 when we are at low speeds. If we are at high speeds, there will be a gamma factor with every mv. Okay? Now let's apply all of this discussion to our cyclotron. Here is our cyclotron. Now these objects in the cyclotron, they are called Ds. This is D number 1. This is D number 2. And they are hollow metals. Suppose Suppose I have a particle of charge q, mass m, that is issued somehow from through thermodynamic emission or by heating particles, hydrogen atoms inside an oven. Okay, so there is some particle of mass m q with some initial momentum p1. Okay, towards the right. Now, why towards the right? Initially, this plate is positively charged and this plate is negatively charged. Okay, so the particle will move towards a negatively charged plate. There will be electric force on this particle. So when it enters this D, this particle enters this D, it has some initial momentum P1. Okay, now all of this arrangement is placed inside a uniform magnetic field. Okay, this is a uniform magnetic field in the region of these D's. Magnetic fields, unlike electric fields, they can penetrate inside metals. There's nothing stopping them from doing that. Alright, suppose this uniform field is B, okay, and it's pointing out of the plane of the blackboard. Now what happens to this particle as it enters this D is that it sees a uniform magnetic field. Inside the metal, it's in the hollow region, it's in this region, inside the slit, inside the hollow region. Here the electric field is 0. Okay, so the only field that this particle is seeing is the magnetic field. And this magnetic field is pointing out, the velocity vector or the momentum vector is pointing towards the right. So a force will act on this particle and it will undergo circular motion exactly in this fashion. So it will move in a circle like this. And the radius of this circle R will be given by the initial momentum divided by its charge and the field. Okay? So this is the initial trajectory of this proton or positively charged particle. Now it leaves the slit, it comes out of the slit. What is the magnitude of the momentum here? क्या momentum है यहाँ पे? आप बताएं. आप पीछे बैठे हैं, आप बताएं. यहाँ momentum क्या होगा particle का? Throughout this region, what's the momentum of the particle? Sorry? ऊंची बोल आवाज में. साथ आप बताएं. So what is this mass into velocity? What is the momentum here? Is it different from this? No. The momentum does not change its magnitude throughout this motion. Okay? Nothing happens to the magnitude of the momentum, right? Because all the forces are normal to the momentum at all times. So whatever magnitude we have here, when a particle is moving in a magnetic field, its linear momentum, the magnitude doesn't change. Its direction may change. So here the particle still has a momentum P1. Now what happens here is that as soon as it issues out of this D and comes into the inter-D region, the electric field switches. Okay, now this was initially a positively charged plate. Now what happens is that this plate becomes negatively charged and this plate becomes positively charged. Okay, now what happens is that as soon as the particle issues out into this region, it sees a negative charge here. Okay, the direction of the electric field in this region is now from right to left, so the particle is accelerated. Its linear momentum goes up. And now the particle enters this D. Its new momentum is P2. In other words, in this region, the particle experiences a force which is purely of electric origin, okay, purely an electric origin force, this gap is really small, so the curving is really small here, but this electric force gives a kick to the linear momentum, and the linear momentum goes up from P1 to P2. So this green represents a kick in the linear momentum. Now the particle has entered the left D. It has a slightly higher linear momentum, P2. This P2 is now higher than P1. Now the particle does not see an electric field any longer, even if the particle, this D remains negatively charged, because inside a hollow conductor the electric field is zero. Now when the particle has entered this D, its momentum has gone up. When the momentum goes up, same charge, same magnetic field, what happens to the radius? The radius goes up. So now this particle will move in this hemisphere or in this D again in a clockwise fashion, but with a bigger radius. Okay? Now, how long does it take for the particle to start from here and come back here? It just takes 2 pi over the omega. So the time period of motion of this particle inside the cyclotron is 2 pi over omega, and this is simply 2 pi over QB m, and this is totally independent of the momentum. So after time capital T, here time is 0 and here time is capital T. I'm just assuming that this gap is really small. Okay, so at time 0 the particle is here, at time equals capital T the particle is here, and this capital T does not depend upon the electric field, it does not depend upon the radius, it just depends upon the magnetic field, it is constant. So the time it takes for this particle is constant throughout the motion. Now when the particle reaches this point, once again the voltage switches on these D's. This becomes positively charged, this becomes negatively charged, and once again this particle, as it comes out into this gap, it sees a gap, it sees a kick. Now the kick is towards the right. So this is the direction of the kick. Its momentum now goes up to some value P3. And it continues its motion now with a higher radius. Okay? So if I draw the trajectory, the approximate trajectory of this particle okay, so what's the approximate trajectory of this particle? Small circle, big, bigger, bigger. Okay? This is called cyclotron motion. So in each round trip, the particle takes the same amount of time, which is capital T. When it has a radius big enough that it is at the outer periphery of the D, then there's an exit port here. What this exit port does is that it allows the particle to go out of the cyclotron. And this particle can then smash nuclei, it can smash other protons, it can smash into other atoms, other molecules, and you can do interesting particle physics experiments with this particle. Okay? So all the acceleration is happening in this region. All the change in linear momentum is happening in this region. Now there are 2 or 3 interesting questions. First of all, I would like you to plot with time how the voltage on the plates should change. How should this change? Right, so square wave, positive, negative, right? Positive, negative, okay. It just remains positive throughout?
The step function.
Step function. You started studying circuits? Okay. Okay. So everyone is drawing these square functions. That's good. But is that the only kind of function you can draw? You can draw. Can you draw a sine wave? Can you draw a sine wave?
I'm not sure, but I think
Any arguments against sine waves? Can we draw sine waves?
omega is varying now.
So most students, a vast majority of students have drawn waves of this kind. The voltage is positive, then it becomes negative. This is T by 2. This is T, right? And this T is simply dependent upon the charge to mass ratio and the magnetic field. So one knows the magnetic field that this cyclotron is bathing in, one knows the charge to mass ratio of the proton, then one can find out what kind of voltage needs to apply. You need to switch the voltage between positive and negative. But is there any harm in drawing a voltage like this? Will this work?
The acceleration won't be linear.
Okay. Mr. Furqan says that the acceleration will not be linear. Will this work? आप बताएं क्या ये काम करेगी? जी क्यों काम नहीं करेगी? कि ठीक है रहनुमा हो तो ऐसा आप बताएं करने दो
इक्वल टू 0 पे वोल्टेज 0 होगा और t by 2 पे भी 0 होगा जब किक चाहिए t by 2 पे किक
स्विच कर रहा है बस स्विच कर रहा है वोल्टेज देखो जी आप बताएं Exactly. It will work because no acceleration is taking place in the region of the Ds. In the region of the Ds, the linear momentum remains constant. The particle is just seeing a magnetic field. No matter how big a voltage you apply here, no matter what voltage you apply here, how big it is, it's not going to affect the particle because the particle does not see any electric field when it's inside the region of the D. No matter how big or small a voltage you will apply, the particle is not going to see the electric field because it's inside the hollow region of a metallic conductor. So the electric field inside the D is always zero, no matter how big or large the voltage you apply. So it's much easier to apply sinusoidal voltages in practice in technological applications because the variation is smoother. A square wave is always discontinuous at the edges. So there can never be a perfect square wave, and if you have large voltages and you're switching between large voltages, there will be lots of sparking. Okay, and the system will be prone to all kinds of errors. So it's always nice to apply these sinusoidal voltages. Okay, so you apply a voltage of this kind onto the plates of the D. Now I would like to look at a numerical example. So in Ernst Lawrence's original experiment, he used a magnetic field of 1 Tesla. This is the magnetic field, and he used a radius of 30 centimeters. 0.3 centimeters was the radius of 0.3 meters was the radius of the D. Okay. Okay, let me check down the numerical values. Alright. Now, with these values of the magnetic field and the radius, what is the time period? It's simply going to be 2 pi over omega. It's B equal to 2 pi QB into M. Okay. From this you can calculate the angular frequency, omega. Okay? So if I calculate frequency, the number of cycles it makes per unit second, this is just omega over 2 pi. Okay? Omega over 2 pi. This is the inverse of the time period. This is simply QB over 2 pi m. This turns out to be equal to about 16 megahertz. What does this mean? This means that if we have a field of 1 Tesla and a radius of 30 centimeters, this was the original design Lorentz built, the particle is making 16 million cycles in 1 second. So it's going around and round in complete loops 16 million times in a second, and its radius is constantly increasing. Okay? What we would like to find out is that when the particle exits this region, what is its kinetic energy? Okay, I would like to find out how much energy has the particle gained, because that's what the particle accelerator is. Okay, how much energy has the particle gained? So I would like to find out the energy of the particle K at the exit port. पहले ही फाइंड करो. किसका? 0.3 मीटर. Can you find out the kinetic energy of the particles as they exit this port? And assume that the particle remains non-relativistic. Half mv squared, good. Now we need v.
Omega square r square m omega half of m omega square r square.
Omega क्या?
और QB is equal to theta
Good. Good. Alright. So the kinetic energy of the exiting particle K is half mv square, assuming that everything is non-relativistic, half m. Now this v square is the square of omega r, right? V is omega r, half m r square. Omega square we've already derived is q square b square over m square. Q square b square over m squared, and this kinetic energy is 2m r squared q squared b squared. Now r, everything is known. Okay, so this kinetic energy turns out to be almost 1 mega electron volts. Okay, 1 mega electron volts. Yeah.
In this example you wrote R is equal to 0.3 meter. What does that mean?
So this radius R, okay? So when you reach the exit port, the radius is this R, okay? So this is the final kinetic energy of this particle. Now the point is really profound here, and I hope you haven't realized this point. I expect you not to realize this point at the outset. What we have achieved here is that a final kinetic energy for the proton of 1 mega electron volts. If you had a proton sitting here next to the positively charged plate, so this is your proton and this is your negatively charged particle, the negatively charged plate, and if you would, this proton is initially at rest. Now a force is going to act on this proton, it will accelerate as it goes towards the negatively charged plate. If you would like the final kinetic energy of this proton to be 1 mega electron volt, how much should this voltage be? कितनी होनी चाहिए? आप तो फॉर्मूले ढूंढते हो, आप फॉर्मूलों के जंगल से बाहर निकले। अब तो कितना वोल्टेज होना चाहिए between these plates to achieve a final energy of 1 mega electron volts? आप बताएं कितनी वोल्टेज होनी चाहिए? कोई बता, आप कर सकते हैं? 1 mega volts. मेगा क्या होता है? Right, you need a voltage of 1 million volts. 1 million volts, 1 megavolts. This will increase the energy from 0 to 1 mega electron volt because the charge on a proton is 1 unit. Okay? So this is the voltage that you would need. In a linear accelerator, if you would like to increase the proton from rest to 1 mega electron volt, this is the voltage you would need. But now we have a cyclotron. The cyclotron does not use this higher voltage. Suppose this cyclotron applies a sinusoidal voltage onto the plates of the D. Time, the voltage, and it just varies between plus 5000 and minus 5000 volts. Right? So it could vary just between 5000 and minus 5000 volts. With such a small voltage, you can you can accelerate the particle through an extremely large potential difference. You can increase its energy to 1 mega electron volt by the application of a small electric voltage, because here what's happening is that there's an interplay between the electric forces in the gap between these and the radius, which is constantly increasing because of the magnetic field. Now if this is the voltage that is applied, one can find out what time would it take for the particle to reach this kinetic energy. In each cycle with this voltage applied, what is the increase in the energy of the particle? So you go from this point to this point. When you cover this length in time, delta t, the particle has started from here and has gone back here. Okay? So this is the initial position and it makes one complete round trip and moves here. So what is the energy that the particle has gained in this complete round trip that I have indicated in yellow? If this is the applied voltage, 10 kilo electron volts. So in one cycle, the energy that the particle has gained is just 10 kilo electron volts. But for a final kinetic energy of 1 mega electron volts, you would need many cycles of this voltage. So the number of cycles that you would need would be 1 mega divided by 10 kilo. Okay, this is 100. You need 100 cycles of this small voltage to accelerate this particle through, so that its final energy is 1 mega electron volts. Okay, so just by applying a small electric field, you can accelerate the particle through extremely high energies. So you need 100 cycles. After 100 cycles of this oscillatory voltage, of this AC voltage, will the particle that has started off in the almost center will come to the exit port, and it will gain an energy that's equal to 1 mega electron volt. And you could not have gained this energy, this much energy, if you just had a linear situation like this, and you need to apply a voltage of 1 mega electron volt, which is really difficult to apply. It's not impossible, we've done this in the classroom, but it's really difficult to apply a sustained voltage of 1 mega volts. Okay, so just by the application of a small voltage that's only plus minus 5000 volts, and looking for multiple cycles of this voltage, the particle will continually ramp up its momentum till its final energy becomes 1 mega electron volt. So this is the advantage of using a cyclotron. Now the same concepts, what we've seen so far is that a particle that is inside a magnetic field and it has some velocity, it will experience a force, a change in its momentum, and it will undergo cyclotron motion. Now my question to you is that if this is the time period QB over M, now if I had relativistic velocities, the particle started off at some small speeds, then it continually increases its speed because its energy is increasing until it approaches the relativistic regime, then this simple formula will not work, because there is a V in the numerator and here there is a factor of gamma. So this factor of gamma will require us to continually change the angular frequency of the applied voltage, or it will continually require us to change the magnetic field as we go along. In the homework I have included one question of this kind. Okay, so what we've seen so far only applies to non-relativistic speeds, that is gamma equals 1. Now the same argument, that is moving particles inside magnetic fields experience forces, also applies to current carrying conductors. If I have, for example, a current carrying conductor, now this conductor is carrying some current density J or some current I. Okay, this is just the motion of charge carriers. We know this. So if there is a force, that if there is a magnetic field that this current carrying conductor is immersed inside, this is a magnetic field, you can actually calculate the force that acts on this current carrying conductor. So the force will be given by, instead of QV cross B, now we will have I dl crossed with B, where dl is a small unit, a small length vector in the direction of the current density. So if this is the current, the magnetic field is upward, a force will act on this conductor out of the plane of the black hole. Okay, so this formula is just another version of QV cross B, because in a current carrying conductor there are a large number of charge carriers. Okay, this also means, okay, let me show you a simple demonstration for this. Now what we have here is quite a simple arrangement. Now if you observe this directly, we have a power supply, we have a wire, there's a resistor that limits the current, this one, and there's a coil of wire, and there are 3 magnets placed close to the wire. So these magnets apply a magnetic field in some direction and the current is flowing in some other direction. Okay, I'll turn on the power supply and see which direction does this coil move. It will oscillate, or it will move in one direction. थोड़ा सा अली, थोड़ा सा इसको साइड से दिखा सकते हो, साइड पे करके थोड़ा सा इधर से, क्योंकि इसने आगे जाना है पीछे। थोड़ा सा जूम कर। ओके, दिस इज फाइन। क्या ये ऑसिलेट करेगा? जब इसमें से मैं डीसी करंट गुजारूंगा, क्या ये ऑसिलेट करेगा? It should move in one particular direction. Now I don't know the direction of the magnetic field as yet, because I don't know the orientation of the so-called north and south poles of these power magnets. You can find out. So So don't try these experiments on your own, unless you're pretty sure what you're doing, because इधर से नजर आएगी, इसको बैठ जाओ, आप बैठ जाओ, नजर नहीं आएगा. Now I am increasing the voltage, the current should go up. Okay, you can see that this coil is being deflected in a particular direction. I have 3 amperes. I'm turning down the current back again. This coil moves back. Now these magnetic forces are actually really weak, so these must be pretty strong magnets, and the current is pretty high, about 3 amperes. So can you tell me what's the direction of the magnetic field? आप बताओ, डायरेक्शन ऑफ मैग्नेटिक फील्ड क्या है? Towards you? No. Upward. So if the magnetic field is upward, okay, the current is flowing in a particular direction. It's flowing from left to right, because this is the positive terminal of the battery. It's flowing from left to right. V cross B. If the B is upward, the force is outward, but the force is now inwards. So the magnetic field is downwards. Okay, so this, at the top we must have the south pole. If I change the orientation of these magnets, okay, now I've changed the orientation, I've just flipped them. Now I increase the voltage. Let's see which direction this coil is going to move. It's going to move in the opposite direction. Okay, so just by changing since the magnetic field, the direction of the conventional current, they are all vectors. Changing the direction of either one changes the direction of the mechanical force that acts on this object. Now my question is that this is a current carrying conductor. Okay, the force is only acting on the current carrying charges, the electrons inside this metal. But why is the metal as a whole moving? There is no force on. Is there any force on the positively charged ionic cores? In the frame of lab frame, there is no force on the positively charged carriers. In the moving reference frame of the electrons don't see a force. It's only the positively charged ionic carriers that are seeing a force. But this is the subject when we discuss the origin of magnetic fields using in the light of relativity. Okay, so now I have another demonstration. Now this is it's a very feeble effect. We've tried very hard to make this work, and I hope it works now. It's an extremely feeble effect. What we have here are 2 wires. In the first demonstration, we showed that if you have a current carrying conductor placed inside a magnetic field produced by another permanent magnet, there is motion, there is a force that acts on the conductor. Now we would like to create a magnetic field through another current carrying conductor. So we have 2 wires, and if these wires carry current in the same direction, there is going to be force acting on the wires. Okay, let's see if we can see this force. But before that, a small diagram on the blackboard. Now, if I have 2 current carrying conductors, both of them carry current in the same direction. This is some current I1, this is some current I2. Okay? So like currents means currents flowing in the same direction. Now if this is wire number 1, this is wire number 2, I would like to see the force that acts on wire number 2. Okay, can I calculate the force? First of all, I will need to find the magnetic field at the location of this wire produced by this wire. If this distance is d, then the magnetic field at the location of the second wire is given by mu naught over 4 pi d I1. If this is a really long conductor, this is a formula that we derived in the first lecture on magnetic fields using the Biot-Savart law. So using this Biot-Savart law, this is the magnetic field at this location B2. Now what's the direction of this magnetic field? Outward. It's into the plane of the black hole. Okay, so the field due to this current, I point my thumb, right hand thumb in the direction of the conventional current, the field has to be inwards here. So the field is pointing into the plane of the black hole. Now I have a charge which is moving with a certain velocity and it's normal to the field. Now what's the direction of the force that acts on this conductor? V crossed with B. The force is directed towards wire number 1. So the force that acts on this conductor is towards the other wire. Now Newton's third law. An equal and opposite force must also be present in this system. That force now acts on this wire. So these two wires must come together. Now remember, this magnetic field is extremely small. देखो ये magnetic field बहुत छोटी है टेस्लास में. If this is 1 ampere, okay, this suppose is 1 centimeters, 0.01 meters. This suppose I just take this to be equal to 10. 4 pi is just 10 roughly. 10 into 0.01 is 0.1. This is 1, so this becomes 10. This is 4 pi into 10 is power minus 7. So the magnetic field is 4 pi into 10 is power minus 6 Tesla. Earth's field is 10 is power minus 4 Tesla. So it's 100 times smaller than the Earth's field. Okay? So that's why if you have a current carrying wire, it's inside the Earth's field, you don't see it deflect. So the force is really, really small. Okay, I'll try to show you this force by passing a large current through two wires. Remember that this experiment, which is being shown in a crude way here, is also the definitive experiment for definition of an ampere. So if 1 ampere is the current that flows through both wires that creates a force of 10 raised to power minus 7 newtons if the wires are separated by a distance of 1 meter. So this is how you define an ampere. Okay? So if you look at the standard SI website, the procedure for defining the ampere is through these current balance experiments. So now I would like to show you this experiment. It's going to be slightly tricky because the forces are really, really small, and I don't know if it's going to show up properly. थोड़ा zoom out करो या zoom in करो जरा थोड़ा सा. ओके, बहुत ज़्यादा हो गया बस. ये कौन से रीजन को आपने जूम इन किया? यहाँ पे ला सकते हो, यहाँ पे. ठीक है, ठीक है, थोड़ा फोकसिंग कर सकते हो. ओके, मैं देखूं पीछे से सही नजर आता है. थोड़ा सा और फोकस करो. अली थोड़ा सा वापस दो. ठीक है. Okay, let's see if these wires are attracted to one another. the wires moving closer? Yes, they are. They finally stick together, okay? So there is force, wires carry current in the same direction. I'm moving back the current. Okay, now the wires are back to their original. Okay, they have stuck slightly, okay? You can see them coming back. ऊपर से नहीं मुश्किल होगा. Okay, let me pass this current back. Okay, मैं दोबारा ये on करता हूँ. Okay, I'm increasing the current. The wires stick together. The current is now 3.2 ampere. It's about 10 amperes, sorry. Really huge current. So I've decreased the current and the wires come back to their original position. One more time. नजर आ रहा है ना पीछे से? यहाँ पे एक मिनट, यहाँ पे थोड़ा सा करो. ठीक है, अब ये जो बड़े डिस्टेंस वाला है इसमें फोर्सेस कम होंगी. ज्यादा करंट नहीं फ्लो करेगा. करंट तो उतना ही फ्लो करेगा जितनी इसकी रेजिस्टेंस और वोल्टेज है, लेकिन फोर्सेस कम होंगी, अट्रैक्शन बहुत कम नजर आएगी. अट्रैक्शन करने के लिए ज्यादा करंट फ्लो करना पड़ेगा. हाँ जी, देखो ना वहां पे. अब मैं दोबारा वोल्टेज बढ़ा रहा हूँ. So the wires stick together where the distance is smaller, and where the distance is larger, the magnetic field is so small that the wires do apply a force, but the force is too small to deflect the wires. Okay, can you move back here? Idhar वापस आ जाओ. इधर लो जरा, इधर. ठीक है, इधर देखते हैं. ये बहुत ज्यादा डिस्टेंस है. Sorry. Okay, I'm increasing the current, the distance between the wires is decreasing. Okay, and then I go back. Alright. So now I would like to finish off my class by one small fact. We've seen so far, what have we done in this course? We've seen the Coulomb's law, E equals 1 over 4 pi epsilon naught Q divided by R squared in a particular direction. देखो ये बहुत important summary है. It's an interim summary of the course. Please pay attention. This is one version of the Coulomb's law. And then we refined the Coulomb's law and stated the Gauss's law. E dotted with dA over some closed surface called the Gaussian surface. This equals the charge enclosed divided by epsilon naught. This is Maxwell's first law. Okay, first equation of Maxwell called the Gauss's law. Okay, both of them we knew are equivalent, but this law has certain advantages. It's relativistically correct, but if you don't understand this, I don't expect you to understand this, but this is just a reincarnation of the Coulomb's law. This is one law that we've studied. We've also seen in disguise a relationship like this, E dotted with dl over some closed path. Okay, if we have static charges, what is this integral equal to? What's the potential difference if you move in a closed path? 0. This is another Maxwell's equation, partial Maxwell's equation. It's partially correct because we're only considering static charges. Okay? This is called the Faraday's law, but only partially correct. Okay, this is a partial Faraday's law. Okay? Now this law tells us that if I have charges anywhere, a distribution of charges, and I make a closed surface around some charges, then the total flux passing through this Gaussian surface will only depend upon the charge enclosed by the surface, and it will not depend upon the charges outside the surface. Okay? This is Gauss's law. One small question: if I want to find the electric field at this point, just this point, will this electric field be dependent upon what these charges are and the configuration of these charges? Will the electric field at this point be affected by how these charges are distributed? Yes, they will be. यार कोई आपको ये तो नहीं कहता कि ये चार्जेस अपना रोल खत्म कर देते हैं. Gauss's law तो सिर्फ ये कहता है कि इस closed surface में से जो flux है, that only depends upon the charges outside. Now this Gauss's law for electricity is dependent on the fact that we can make positive and negative point charges. Okay? Because the electric field starts at positive charges and sinks or ends or is subsumed by negative charges. So it assumes individual distinct positive and negative charges. दो किस्म के charges को की बुनियाद पर ये Gauss's law काम करता है ना? तो दो तरह के charges exist करते हैं, electric charges. लेकिन there are no magnetic charges. There are no magnetic monopoles. Okay, you cannot have a separate north pole and a separate south pole. Wherever there is a north pole, it has to be accompanied by a south pole. So scientists are trying really hard to find these magnetic monopoles, but they don't exist so far. So if I would like to write the Gauss's law for magnetism, which is the third Maxwell's equations, we've already seen two. The third Maxwell's equation, which is the Gauss's law for magnetism, states that B dotted with dA, just the complete analog of this, you over any closed surface, this must equal, what must this equal to? 0, because there are no magnetic monopoles. So this is the one of the Maxwell's equations. So we've already seen three equations. Three of the four equations. So we're almost 60-70% of the course is almost done. So this is the Gauss's law for magnetism. And what it means is that if I have any closed surface and I have sources of magnetism. Sources of magnetism are magnetic dipoles. I have these magnetic dipoles anywhere in space, pointing in random directions. Okay? Then I take any closed surface. The total magnetic flux through this surface has to be always equal to 0. Flux that enters a closed surface must leave the closed surface, because field lines cannot end or start anywhere because there are no magnetic monopoles. So in the next lecture, which is going to be next Monday, this Friday, we're going to see what happens if we have B dotted with DL. Okay, we've seen E dotted with DL. What happens when we have B dotted with DL? This is called the Ampere's law. So see you on Friday, inshallah. Thank you.